Welcome to the last session of the NISQ workshop. Our first speaker will be Elizabeth Crosson.
Thank you. Thanks to the organizers for the chance to speak at this workshop, and thanks to all of you for sticking around for one of the last talks of the workshop. So what I'm going to be talking about today is quantum annealing, which is a heuristic quantum algorithm that is by now a few decades old, but it's an idea that's still around and it still has a future. So I'm going to tell you a bit today about what we expect in the next couple of years, both on the hardware side, although I'm not so much an expert in that. I'm a theorist, so I'll tell you how we as theorists are trying to evaluate what's coming next in this world of quantum annealing. So quantum annealing should be regarded as a predecessor of today's NISQ era algorithms because it is a heuristic for combinatorial optimization that is well suited towards to being implemented with analog quantum hardware. So quantum annealing was well motivated early on when it was first proposed by comparison and contrast with classical simulated annealing, as well as by this evidence for some inherent robustness to noise in its analog implementation. I know many people are already familiar with this idea of quantum annealing, but I'll include some mathematical definitions in a few slides. But when I say that we have this notion of comparison and contrast with classical simulated annealing, I mean that both algorithms are motivated by the tendency of physical systems to find low energy states, really quantum annealing differs from classical simulated annealing by replacing random walk or thermal fluctuations with quantum fluctuations. So there's a similarity between them. Classical simulated annealing has been widely successful. So this was strong early motivation. But despite this, there has been to date no theoretical evidence for an unqualified asymptotic quantum speedup in optimization with quantum annealing, despite this long history. And even aside from theoretical evidence, well, it's a heuristic, so we would also be happy to see empirical evidence. But benchmarking studies of quantum hardware, which are now up to over 2,000 qubits and soon to be many more in hardware provided by D-Wave, have not produced. I think we can summarize the story. It's been a long, interesting story, but we can summarize it by saying we so far have not seen convincing evidence for a practical quantum speedup in useful optimization tasks. So why haven't we found a speedup? Well, one sort of meta excuse is that it's challenging to prove asymptotic speedups in general, including for classical optimization heuristics that turn out to work very well in practice. So for example, classical simulated annealing is really based on the Metropolis algorithm. But the Metropolis algorithm was developed in the 40s and 50s, whereas simulated annealing was not proposed and accepted until the 1980s. So what's the difference? Well, in the 80s, there was a conceptual kind of leap between the two. But in the 1980s, that's when we got fast digital computers. So people could just go and try out the idea and find out that it worked really well in practice. Okay, but kind of more specific to the case at hand, we have the fact that current quantum annealing hardware produced by D-Wave, I would say it's very technologically impressive, but like all NISQ systems, it suffers from noise. That's part of the name. That noise may be obscuring our detection of a practical speedup. So that's one possibility. And then there's a third possibility that people often point to, which is that quantum annealing hardware based on transverse Ising models, they generate equilibrium states of what are called Stoquastic Hamiltonians. There's a typo, sorry. Stoquastic Hamiltonians, which are known to have reduced computational complexity. So the issue of noise, we know, one way to deal with that is to say, well, eventually one day that can be solved by fault-tolerant digital quantum computers, say gate model quantum computers, that are capable of at least benchmarking idealized versions of quantum annealing using Hamiltonian simulation. So once we have this, it sort of decouples the algorithmic idea of quantum annealing from any particular analog hardware implementation. So in the far future, we will at least be able to properly test this algorithmic idea. So in this talk, I'm going to focus more not on the noise issue, but on the complexity issue. So this idea of stochastic Hamiltonians. So in general, the complexity of stochastic Hamiltonians is actually not completely pinned down, but rigorous classical simulations are known to exist in some cases, and we also have an algorithm called simulated quantum annealing, for which empirical benchmarks so far strongly support this idea that a wide class of these systems can be classically simulated. Now, adiabatic computation, which is kind of like a theoretical, idealized version of quantum annealing, I'll clarify that soon, is known. It's known that with adiabatic computation in general, that it can be BQP complete when you use general local Hamiltonians that are not necessarily stochastic. But one thing that I want to bring to your attention is that non-stochastic quantum annealing, even if it's unlikely to be classically simulable, it's not attempting to do the same thing as this kind of universal adiabatic computation. In one case, you're trying to produce a highly entangled ground state that's the output of a quantum computer. But in the other case, in the case of optimization, you're just trying to find bit strings that solve some classical optimization problems. So this notion of BQP completeness actually doesn't directly tell us anything about whether quantum annealing with non-stochastic Hamiltonians could be advantageous for optimization. So I'll start by kind of explaining the original and simplest proposal for adiabatic optimization, and it's called transverse-field adiabatic optimization. So the idea is that we have some cost function that is diagonal in the computational basis, or that is the cost function is f, and we embed it into a Hamiltonian that's diagonal in the computational basis. And if you want to be able to implement this with physical interactions, you might ask that f of x can be kind of expressed locally in terms of, say, Pauli-Z operators. And you could encode kind of constraint satisfaction problems like max 2-sat in a form like this, so that the ground state of hf corresponds to a bit string that encodes the solution to an NP complete problem. And so the way that you're going to try to produce this bit string is by initializing the system in a transverse field. So this initial Hamiltonian is just minus the sum of the Pauli-X operators, and the initial state is the ground state of that Hamiltonian with every qubit in the plus state. And the idea is we're going to interpolate from this initial Hamiltonian to the final Hamiltonian along this linear interpolation schedule. And the adiabatic principle, or really the adiabatic theorem, guarantees that if we do this interpolation sufficiently slowly, say for time that scales polynomially in the number of qubits, and the inverse of the minimum spectral gap between the ground state energy and the first excited state energy along the evolution, that this will suffice to be in the ground state of the system at s equals 1, and therefore find the minimum of the function f. Now, of course, we don't expect to be able to solve worst case NP-hard problems in polynomial time with the quantum computer, but like all heuristics for optimization, we're hoping for good performance in practice, maybe on average. So how do we go from adiabatic optimization to quantum annealing? Well, QA generalizes QAO to include diabatic effects and or thermal dissipation. I should say that definitions in the literature can vary quite a bit, but the essential point is that quantum annealing is based on a linear is based on the same kind of interpolation of Hamiltonians, but that you're not required to be at zero temperature, you're not required to remain in the ground state, and in some cases this can be very beneficial. So this idea that the runtime of the algorithm scales with the inverse of this minimum spectral gap is sufficient but not necessary to be in the ground state at the end of the evolution. But kind of the problem with these more general proposals of quantum annealing is that we lack such a nice theoretical kind of quantity like the spectral gap that predicts the time to solution for that version of the algorithm. And so, most studies of quantum annealing that are not matched with quantum adiabatic optimization will rely on sort of empirical benchmarking. Okay, so now since the minimum spectral gap always occurs somewhere in the middle of this interpolation, a standard proposal for generalizing transverse field quantum adiabatic optimization is to turn on an extra Hamiltonian somewhere in the middle, right? Because the initial Hamiltonian is classical and the final Hamiltonian is classical, so both of them have a large spectral gap. So, let's turn on this extra Hamiltonian in the middle. And hopefully, maybe in some cases, that might increase the spectral gap. So kind of now there's this s times 1 minus s that is maximized when s equals a half. And this extra Hamiltonian is typically taken to have the same locality structure as the final Hamiltonian, or the cost function itself. And it is known that, at least in some examples, including an h extra, can make a huge difference. It can change the problem from having an exponentially small gap to having a large gap that's independent of system size. But in general, we have relatively few strategies for guiding our choice of this h extra. So the most commonly analyzed proposal is just choosing it randomly, choosing it to be a random local Hamiltonian. So we'll take this form as our definition of QAO. I really want to get across that quantum adiabatic optimization is just one type of adiabatic algorithm. It's a type of adiabatic algorithm where your final Hamiltonian is classical. You're trying to solve a optimization problem. And so the main question in this context is whether general h extra can improve the runtime of the algorithm compared to this limited class, which I'll describe in more detail, that are called Stoquastic Hamiltonians. These Hamiltonians that are on the border of classical and quantum complexity. So, okay, so let's talk about Stoquastic Hamiltonians. Local Hamiltonian is stochastic if there exists some choice of local basis B in which every local term has real and non-positive off-diagonal matrix entries in that basis. And the name stochastic combines quantum and stochastic because if H is stochastic, then G is a matrix with non-negative entries in the basis B. And in physics, these Hamiltonians are said to not have a sign problem. So it's an idea that goes back over 50 years. In mathematics, the study of non-negative matrices goes back much further. Now, since G is defined this way in terms of H, the ground state psi of H is the principal eigenvector of G, the eigenvector with the largest eigenvalue. And since G has non-negative entries, so does G to the power L for any positive integer L. So if we take this limit of G raised to some large integer power and we normalize it, then this is a sequence of non-negative matrices, right? This limit comes from such a sequence, and so it must converge to a non-negative matrix. And so indeed, this projector onto the top eigenvector of G is a non-negative matrix. Here I'm assuming the top eigenvector is unique, as we often do in this adiabatic context. And so there is some global choice of phase for which this ground state eigenvector has non-negative amplitudes in the basis B. Okay, and that's a proof of the Perron-Frobenius theorem. So in other words, what we're saying is that the components of this eigenvector are non-negative. And a very similar argument also applies to the amplitudes of the thermal density matrix, which describes a system in thermal equilibrium. Okay, so stochastic Hamiltonians are common in nature because any system of either bosonic or distinguishable particles moving in space and interacting via a scalar potential is stochastic in the position basis. But in quantum computing, we're more used to dealing with the context of spin systems. And there we have generalized transverse Ising models, such as those used in transverse-field quantum annealing. We can see that they are stochastic in the computational basis, right? Because the condition is that the off-diagonal matrix entries are real and non-positive, and this will be satisfied in the computational basis where all of our off-diagonal matrix entries come from these Pauli-X operators. Here I've kind of stipulated that these local transverse fields are greater than 0, but really you could let them have arbitrary sign and use local unitary transformations that wouldn't affect this part to give these all the same sign. So not only is this case happen to be stochastic, but in a sense we can reduce any stochastic adiabatic computation, at least anyone that uses local Hamiltonians with bounded interaction degree, so at most a constant number of terms acting on each qubit, to one that, so any such stochastic adiabatic computation can be simulated by an adiabatic computation with just generalized transverse Ising models. And, so this is a reduction using perturbative gadgets. Okay, so when we have a stochastic Hamiltonian, so what is this business about classical simulation? So now I'll describe how those algorithms work. So when we have a stochastic Hamiltonian, what we do is we expand the partition function as a path integral in the basis in which the Hamiltonian is stochastic. So, here the partition function is a trace, which we can, here we've written the definition of the trace and split up e to the minus beta h into a product of several pieces of e to the minus beta h over L. And then in this step, you kind of have inserted several complete sets of the identity, resolutions of the identity in between the factors in that product. And since this kind of propagator between elements of the path is itself just a non-negative matrix, every path makes a positive contribution to this sum. So therefore, we can define a probability distribution over the space of paths. So here is a proper probability distribution. And the idea of path integral Monte Carlo, which is a classical algorithm, is to use a Markov chain Monte Carlo procedure to sample this distribution of paths. So anytime you have a distribution for which you can efficiently compute the probability density up to some normalization factor you may not know, you can use something like the metropolis rule to define a Markov chain and do Markov chain Monte Carlo. But of course, that doesn't tell us how long such a procedure would take to converge. But at least it gives us something we can just immediately write down in a computer and try it out. Okay. And this path integral Monte Carlo algorithm is the basis for what is called simulated quantum annealing. So simulated quantum annealing is this practical heuristic that is used to simulate transverse field quantum annealing, both at 0 temperature or at finite temperature. And it is based on discretizing the adiabatic path, so this parameter s that goes from 0 to 1, into a bunch of small steps, s1 through sm, and running path integral Monte Carlo at each step of that path. So at each step si, the idea of, so what changes with simulated quantum annealing is that you want to use a configuration sampled from the distribution at the previous step as a warm start, as a starting configuration for the path integral Monte Carlo, path integral PIMC Markov chain at the current step si. So although these warm starts seem to be essential in practice, if you talk to the people who are successful at simulating these results, it's a bit of a puzzling situation with regard to the theory, because theory tells us that the warm starts in this context won't change the convergence by an exponential factor. That is not for generalized transverse Ising models. Yet classical simulations must depend on the entire adiabatic path to avoid kind of skipping over it and trying to solve NP-hard problems in polynomial time. So one thing that makes this problem so interesting is that similar complexity considerations and counterexamples rule out general rigorous simulations of stochastic quantum annealing based on all known methods. So if it is possible to classically simulate this algorithm in general, then new methods are needed. So that brings us to non-stochastic Hamiltonians, which at this point are the great hope for quantum annealing. And so while this question of rigorous simulation of stochastic Hamiltonians remains open, the empirical success of SQA has largely convinced the community, all but the most diehard theorists that demand a rigorous proof, but most of the community isn't that demanding, and they are convinced that we are unlikely to find quantum speedups with stochastic quantum annealing hardware. So at the 2019 APS March meeting, D-Wave announced the implementation of non-stochastic Hamiltonian couplings in their superconducting flux qubits. And similarly, one of the primary goals of IARPA's Quantum Enhanced Optimization Program is the development of non-stochastic quantum annealing hardware. So this has very much become the focus in the near term for the future of this subfield. So with non-stochastic hardware very likely to be on the way, the job for theorists is to determine whether or not it is likely to at last provide a quantum speedup in optimization. So this brings me to a technical part of my talk where I tell you about a new technical result we've been working on, which is a notion we call de-signing. And it is a map from non-stochastic Hamiltonians to stochastic Hamiltonians. So given a general Hamiltonian, which here I'll write in terms of its matrix entries. Sorry that I'm kind of moving back and forth between matrices and operators. It's clear that this is a kind of a basis-dependent talk. We'll de-sign it into a corresponding stochastic Hamiltonian. So in other words, we'll just do an entry-wise operation that makes all of the off-diagonal matrix entries real and non-positive. And so this element-wise mapping is totally nonlinear, and in general, it's going to alter all of the eigenvalues and eigenvectors. So in what sense is this mapping a useful correspondence? So the answer is that the mapping makes particularly good sense to consider in this context of adiabatic optimization. So because our initial and final Hamiltonians in adiabatic optimization are both stochastic and in fact classical, this mapping takes every not stochastic path to a stochastic path, right? So we can compare them in a one-to-one manner. And so, okay, so even that in itself isn't necessarily tell us anything, but the value of this comparison is in a surprising observation that de-signing almost always increases the size of the spectral gap above the ground state. So you start with a non-stochastic Hamiltonian, you de-sign it, and the spectral gap almost always gets larger. And so this observation is supported by a series of arguments. And I should say the statement holds true with high probability. So here are some supporting evidence for this. So we have a rigorous proof in the setting of random matrix ensembles. And we also have results based on the spectral theory of signed graph Laplacians that apply to certain classes of sparse matrices. And finally, we observe a very clear trend in numerical simulations that already emerges at low bit number. So what I'll tell you about mainly is this proof in the setting of random matrix ensembles. So, but actually first let's make some kind of initial preliminary observations about this de-signing operation. So de-signing always decreases the ground energy. And the way that you can see this is that if you start with the ground state of your original Hamiltonian, then you can define this psi bar just in terms of the absolute value of its amplitudes of the original ground state, and you can use it as a variational state. You can use it as a variational state with the d-signed version of the Hamiltonian, right? So that must upper bound the ground energy of the d-signed Hamiltonian, but at the same time, it must. You can just see by direct calculation that all of these being the same sign, you get as well. Yeah. So basically, a triangle inequality gives you this step because you've taken all the components of the matrix vector sum and made them all in phase with one another. And so if you take this and you combine it with, well, we can just assume our Hamiltonian is positive semi-definite, then then the de-signing operation leaves the trace unchanged, because if the Hamiltonian is positive semi-definite, then all of the diagonal entries have to be non-negative. So the trace is unchanged, but the trace is also the sum of the eigenvalues. Here the ground state energy has decreased. The sum of the eigenvalues is the same, and that tells us that we must have increased the spacing somewhere. We must have increased the spacing between eigenvalues at least somewhere in the spectrum. So the question is, does that happen near the ground state? Well, here's why it does in the context of random matrices. So random matrices. So let's start with something many of us are familiar with. So let's do an n by n random symmetric matrices with IID entries of mean 0 and variance 1. So if these entries are Gaussian distributed, this is called the Gaussian orthogonal ensemble. And Wigner showed that the distribution of eigenvalues of these matrices is a semicircle that goes between plus and minus root n in its particular normalization. And maybe not as well known is that this fact about the Gaussian orthogonal ensemble also holds if we chose the entries uniformly in the range -1 to 1. And this is part of a sort of universality of this semicircle distribution, only depending on the first few moments of the probability distribution that governs the entries. So now, since there are n, so that's the version we're actually going to use in our argument. Since there are n total eigenvalues, and they're between root n and minus root n and plus root n, then the average spacing between them then is like 1 over root n. And so you can, kind of eyeball the gap, right, between the top. So we're gonna look at the top of the spectrum. So you can eyeball the gap as about 1 over root n, and then all kinds of things are known from the random matrix literature, like large deviation bounds for that spacing. Okay, so to compare this with the case of stochastic Hamiltonians, there we had general real symmetric matrices. So let's compare this to the case of stochastic Hamiltonians. So here, to do that, we're going to define an ensemble of symmetric matrices with non-negative IID entries, chosen uniformly in the range 0 to 1. Okay, and so here's the key point. So each matrix in this new ensemble of non-negative matrices can be obtained from a matrix in the previous ensemble by adding a matrix with a 1 in each entry. So a giant matrix with a 1 in each entry, and you just shift things up and then divide by 1/2 if you want to normalize it. So this rank 1 shift, what it's going to do is turn the largest eigenvalue into an outlier. Because this matrix that has a 1 in every matrix entry, it's got a single eigenvalue n, and all the other eigenvalues are 0. Okay, so you can start from that matrix and consider the other real random matrix as a perturbation, right? But all of its eigenvalues are between plus root n and minus root n. So you start from your top eigenvalue of the matrix of all ones. You can at most decrease that by root n. You can at most, and then you go to the second eigenvalue, which is 0. You can at most increase that by root n, right? And so the gap then of the non-negative matrix ensemble, the typical gap should be like n minus order n to the 1/2. So in other words, you still have a semicircle, but you've kind of kicked out the top eigenvector to become enormous, right? And so now your spectral gap is this enormous difference between this one top eigenvalue and whatever comes next, whereas in the real symmetric case, you have this very small spectral gap. So in the random matrix case, then it's completely clear that this de-signing operation increases your spectral gap dramatically with extremely high probability. So the main question that remains is whether this also holds for local Hamiltonians. There we do have some results, but they're a little complicated to tell you about. And then we also have some numerics. I want to acknowledge my co-authors, and Tamim, Itai, and Peter, and we are part of the IARPA Quantum Enhanced Optimization Program. So what we do in the numerics is we find that the fraction of non-stochastic paths that are superior to their d-signed counterparts, we find that going to 0 rapidly with system size. But we do notice that there are exceptions. With some probability, there can be exceptions. Of course, we're trying to understand those as well. So here I've got kind of one more slide that I just kind of want to give you some perspective that comes out of this subfield of quantum annealing and all of its negative results over the years. And in fact, negative results in adiabatic optimization are not a recent development. They've been around since the mid-2000s. Yet it's always possible to tweak the algorithm, usually by pinning our hopes on something that we can't immediately analyze. So that makes it sound like that we're going after something unfalsifiable, or every time you try to falsify it, it's a moving target. But I want to also advocate the other point of view, which is that looking back, what should we have done differently with quantum annealing? The development of QA hardware was perfectly well motivated from the beginning, and it remains entirely possible that it'll find a purpose. If not in optimization, maybe in analog simulation. Actually, some very nice papers by D-Wave in the past few years have simulated 2-dimensional and 3-dimensional condensed matter models have done analog quantum simulation for those using their device. So, one lesson, I think, that we can learn from quantum annealing is that, we had this conjecture for a long time about simulating stochastic Hamiltonians, and we were too slow on solving it. Because, sure, we proved some limited cases, and we came up with all these arguments, but we also needed help from people who were doing, benchmarking. And so, in general, I think for the evaluation of these NISQ-era heuristics, it's actually going to be a long-term interplay between, theory, benchmarking, applications, and experiment, all different communities with different standards for what is considered a convincing argument and different goals. And then, another lesson that we can take from this long history of quantum annealing is that we don't have to force ourselves to be positive about this stuff all the time, because ideas that are already considered compelling, they've built up momentum and they're not stopped by just a bit of bad news. So what I want to say is don't be afraid to report on results if you find them that rain on the parade a bit, because we should keep our standards high. This is a long-term exercise. I say don't forget who we are, because I think this is a great community, and although this is a very exciting time, we shouldn't lose sight of our core principles. I liked Jake's comments on the first day that we should align our interest with that of the stakeholders. But I think it's also important to remind them to be patient if we want to one day get to the truth. Thanks.
Do we have any questions?
So, do you know how your designing procedure, how it works with frustration-free Hamiltonians? So, is it better, or does it give
With the what of the Hamiltonian?
frustration-free Hamiltonian?
With the frustration-free Hamiltonian. So let's see. So here you would start with a non-stochastic Hamiltonian, and you would de-sign it and hope that the resulting Hamiltonian somehow ended up as frustration-free. I think that we would that would be a very special case, right? So if one version of the Hamiltonian was frustrated, it would be extremely special for both the original Hamiltonian and its d-signed counterpart to both be frustration-free. I wouldn't expect that to happen because of the. Actually, I can say even more. So here you can actually you can essentially prove that this should be a strict inequality by demanding that there is no unitary transformation that forces the that cures the sign problem for the original Hamiltonian. So if you assume there is no diagonal unitary transformation that cures the sign problem, this inequality actually becomes strict, and it would be impossible for both the original Hamiltonian and its d-signed counterpart to both be frustration-free. So.
Other questions? Well, I'll ask one.
Sure.
In the numerics that you were doing for local Hamiltonians, the cases that you're seeing where this designing does not improve things, are you seeing any patterns, anything like that?
Yeah, that's a great question. So first of all, when designing fails to increase the gap, it never decreases it by much. Like for example, in what we've seen up to 20 qubits, it never decreases it by more than maybe a factor of 4 or so. As for whether there's a pattern, I'm sure there's something interesting to be found there. Why? I should say, so the ground energy always gets lower, and so if it were as simple as saying that the first excited energy goes up, then we'd be done. It'd be possible to make a very clean statement that this always increases the gap, but that's not what happens. The first excited state energy sometimes goes down, I think the best lead that we have at present is that it's related to anti-symmetry of the wave function. These cases where the non-stochastic case can be better seem to be related to anti-symmetry under certain reflection operators.
Other questions? If not, let's thank Elizabeth again.